Hi there, I'm planning to get a variac for my lab, which is a mains transformer allowing the selection of a variable output voltage. To control that output voltage and the current drawn by the load, I looked for an AC panel meter and I picked this one from an eBay seller, 22 Home Easy Buy. If you're familiar with my videos, you know that I got a similar module earlier and made it into a power meter. I put a link to that video in the description. I could have bought that same module again, but I like this one because I don't want to monitor energy, and I figured the discrete 7-segment display is easier to read from wider angles. The specs on the sheet that came with the meter are pretty impressive for the price, and it has a fairly high resolution, quite a bit better than the module I used before. Both, however, have the same issue that they stop working when the voltage falls below 80 volts. I have the 80 to 300 volts model, by the way. The 80 volt limit is a serious problem if you want to use the meter in a variac because the voltage can go all the way down to zero. Clearly a display that only starts when you exceed 80 volts would be pretty useless, but I figured there had to be a way to change that, and indeed there is. In this video I show you how to modify this meter so it can measure from 0 to 300 volts AC. At this stage, please note that this meter measures and uses mains voltage. Moreover, everything inside this meter is at a dangerous mains voltage level. If you use or modify the meter, you do so at your own risk. The wiring diagram is straightforward. It's also printed on the back of the unit itself. The current transformer, shown as CT here, comes with the unit and is of the closed ring type. It says here on the bottom that the unit is for 50 Hz and does not support square wave or other inverter outputs. I have seen that other eBay sellers state that the same unit is rated for 50 or 60 Hz, and I will show that it works with 60 Hz just fine. The problem of square waves and other non-sinusoidal waveforms could be more of a current transformer issue. Here's the module and the current transformer as they come out of the box. I then did a quick wire up and tested it, and it worked fine, but I wasn't interested in using it without the low voltage modification, so I went straight into that. With the help of a spatula, I removed the back cover, and with considerable effort I managed to get the front cover off as well. The electronics consist of two PCBs in a sandwich configuration. I can see some interconnecting pins between the two boards. The pins look rather messy, hand soldered. The top board with a big red capacitor and large power resistors is probably handling the power supply for the actual main board below. Another set of 2-pin board-to-board interconnects on the other side. To see what's going on between the boards, I decided to connect it back to AC to do some measurements on those pins, but to my surprise, it no longer worked. I got just zeros on the display and neither voltage or current readouts. The flickering is because of the camera shutter. You can't see it on the real display. Great, now this modification video has become a repair video too. I had hoped not having to desolder the interconnect pins, but now I had no choice. It's the only way to get access to all areas for fault finding. And while the boards look reasonably from a distance, the manufacturing is pretty horrible on close inspection, as you will see shortly. I started by reverse engineering the schematics of both boards. Here's the schematics of the upper board, which is mainly the power supply in typical capacitor dropper configuration. By the way, I have seen pictures of other DL69-2048 on the web where the power board looked slightly different in the component arrangement, so you may have to adapt my description a little. AC mains comes in and one side, arbitrarily labeled live by me, hits a big 820 nanofarad capacitor, the big red one, with a 1 megohm discharge resistor in parallel. You may be able to see this discharge resistor faintly between the cap and the input connector. Then there's a big 51 ohm resistor in series before the mains voltage, reduced by the voltage drop over the capacitor and the series resistor, feeds the full bridge rectifier down here. The positive output goes into a large 10 ohm resistor, which sets the current for two Zener diodes in parallel, obviously to reduce the heat. Two large electrolyte capacitors and two ceramic capacitors do some smoothing and filtering on the 5V output on the board-to-board connector J6. The power supply works, but its schematics strikes me as extremely odd. Putting two Zeners directly in parallel for load sharing does not work in practice. Even if they are the same type and manufacturer, one will always conduct slightly earlier and will have almost all of the current. It is also unnecessary. I measured the mains board to use slightly less than 50 mA at 5 volts. That means the loss in a single Zener diode would be around 250 milliwatts. This is totally within the specs of most Zeners of this form factor, which is usually 400 to 500 milliwatts. Also, the 10 ohm resistor could be replaced by a simple 1/4 watt type because it dissipates just 25 milliwatts. Then there are two different Elcos, one rated 16 volts and a smaller one rated 10 volts, but they are both in parallel, so there is no reason why they should have different voltage rating. It almost looks as if the 16 volt types was intended to be connected directly after the bridge rectifier before the 10 ohm resistor, and that would make much more sense, but that's not the case. The weirdness doesn't stop here. Why the 51 ohm resistor? At 50 Hz, the big capacitor has a reactance of almost 3900 ohm, so the additional 51 ohms in series makes hardly any difference. And it's again grossly oversized. It looks like a 3 or 4 watt type, but there are just 3 volts voltage drop across it, and so the dissipation is less than 180 milliwatts. But oversizing is better than undersizing, so this power supply stays very cool, apart from the big capacitor, which gets to about 40 degrees because it drops about 220 volts at slightly below 60 milliamps. What a strange power supply. But it does produce 5 volts, and obviously, since the display works, that's not the problem. The other function of this board is to get the AC mains voltage for measurement. This is done through a chain of 6 200K resistors in series, so 1.2 megohm in total. They use that many resistors because tiny SMD resistors are not rated for mains voltage, so by using 6 of them in series, each needs to handle only 1/6 of the voltage. I tested the path from the mains connector to the pin labeled volts on the J5 connector, and everything is fine. If that were broken, it would explain the 0 volt reading, but in any case, not the zero current measurement. The current transformer is handled also on this board, but very simply. Just a 1.4 ohm resistor in parallel to the transformer and a resulting voltage drop goes to the remaining 2 pins of J5. I labeled them Cur A and B. Note that the third board-to-board interconnect, J4, is not connected to anything. It's only there for mechanical support. Here's a rough overview of what's on the main board. The brains is obviously a microcontroller of some sort. I have not managed to find anything about this chip. What you see here is what's written on it. The actual AC measuring and calculations are all done by this chip, an HT7017. I managed to find a Chinese datasheet for it, which was key in finding the problem. From the limited information that I managed to extract using Google Translate, this is quite an amazing chip, probably for smart meters with a 22-bit ADC on board. It is driven by a 6 MHz oscillator here. The last chip is that big one, TM1640. It's a LED 7-segment driver that can handle up to 16 digits. In this application, they are spread across 3 different readouts for voltage, current, and real power, apparent power, and the phase angle. I indicated where the matching board-to-board interconnects are from the power supply board. Giving the missing datasheet for the microcontroller, This schematic is somewhat incomplete, but the key things are there. From the fact that the display was working, but just showing zeros, and the number of zeros changed when pressing the button when cycling through the different modes, we can deduce that the TM1640 is working, and so is the microcontroller. It clearly responded to button presses and sent varying display formats to the TM1640. Having the boards separated made debugging a lot safer and easier because I simply applied 5 volts from my lab power supply directly to the corresponding interconnect of the main board and did not use the power board at all. This of course meant I had to simulate the volts and Cur A and B signals. I traced the volts line and the Cur A and B lines from the interconnect to the pins of the HT7017. Of note, you can see that the volts connection is terminated by a 1.2K resistor. With a 1.2 megohm resistor made of 6 200K resistors on the power board, this forms a simple divide by 1000 voltage divider. This means 250 volts AC should be just 250 millivolts AC on pin V3P of the chip. This I applied for my function generator, but no success. I then checked the HT7017 TX and RX lines with a scope and found that the TX pin was steady on high level, but the RX pin was very busy. Obviously the microcontroller trying to send data but did not get a response because the HT7017 was playing dead. This led me to check the reset or RST pin, and that was constant low. According to the datasheet, RST is active low, that means the chip was constantly held in reset. By turning the power off and using a multimeter, I saw that the reset line had a 0 ohms connection to ground. Aha, now we are getting somewhere. Time to break out the microscope and follow the RST line. I found it led first to a combination of a 4.7K pull-up resistor and a ceramic cap to ground, and then to a pin on the microcontroller, probably an output to allow the controller to reset HT7017 as well. The idea of the resistor and cap is that at power up, the discharge cap holds the reset line low until it's charged by the 4.7K resistor to 5 volts and then releases HT717. Well, it turned out this capacitor was now a dead short. I mentioned before that the board looks horrible at close inspection. Here's a brief tour. We start with the 1.2K resistors and capacitors at the input of the HT7017, which comes into view now. The cap C7, which you see now, is the one that turned into a 0 ohm resistor. Next to it is R1, the 4.7K pull-up on the reset line. The top of the TM1640 with lovely hand soldering next to it. U4 is the unknown microcontroller. With all the gunk and solder splatters on the PCB, I thought the silvery line on the cap was maybe a dislodged sliver of solder residue or a stray piece of wire, but scraping did not remove it. Need to get closer for better magnification. And need to refocus. It's clearly a crack with lots of tiny hairline cracks around it. Well, there's no alternative but to remove the cap, which I did. Now, the truth of the matter is that so far I have avoided stocking any SMD caps or resistors, so I haven't got anything to replace it with. I just ordered a book of SMD capacitors, but it will take time to arrive. At least the short is gone, and since the HT7017 reset line is also connected to what it looks like an output of the microcontroller, the board now works without a cap. But why did it work initially when I received the unit and was dead after I had removed it from the housing? My theory is that in taking the boards out, I stressed and slightly flexed the main board. You see, there are these small noses along the side of the PCB. These need to slot into the corresponding holes in the front cover. In taking the board out, you need to bend the plastic of the front cover, but I must have also slightly bent the main PCB, which may have stressed the capacitor and caused it to crack. Time for a quick accuracy test. Because the power board is not used except for its current transformer circuit, I made my own 1.2 megohm resistor on the breadboard using 1 meg and 2x100K in series. The main board is powered from my bench power supply, and I'm using my AC transformer to provide AC volts and current. To improve readability, I use the front cover in reverse. 2.1 volts AC and 80 milliamps current. The current is a little off, but that's normal at such low currents. To save time, I show the testing of other voltages and currents sped up. Because the AC comes from a transformer with different taps, voltage and current drops to zero briefly every time I select a different voltage. 25.8 volts is the highest voltage this transformer can produce, and the current through the test resistor is 0.95 amps. The module readouts are very close, and it has no problem measuring and showing very low AC voltages. With that problem out of the way, it's high time to get to the promised modification. If you recall the schematics of the power board, it is clear that to make this unit measure from 0 volts onwards, we need to disconnect the voltage measuring input from the AC mains input. There are a couple of ways of doing this. One way would be to cut this track here and then solder your own combination of resistors, making up a total of 1.2 megohm, to this pin leading directly to the mains board. That modification can be done without desoldering the power board from the mains board. The 1.2 meg can be made like I showed earlier by 1 meg and 2 times 100K if using standard through-hole resistors, which have a higher voltage allowance than the SMD types and could be put into heat shrink tubing to keep them safe. It's a problem, of course, where to put those resistors and how to get the connection to the outside done. If you have steady hands and the right tools, it just might be possible to reuse the SMD chain of resistors without desoldering the power board. In this case, the cut and connection point would be here, almost under the 51 ohm resistor, which makes it really awkward to work. And keep in mind that compared to the previous case, a simple cut is not good enough. A real gap of 5 mm or more needs to be made to safely separate the volt sense connection from the full mains voltage. You could, of course, cut one end of the 51 ohm resistor, lift it up to give you the space to work, and afterwards bend it back down and resolder the cut. Since I had the power board disconnected already, I decided to use another method. I selected to keep the SMD resistor chain and cut the trace under the capacitor instead, and at the same time replaced the 2-terminal mains input connector with a 3-terminal one to have a neat connection for the new separate volt sense input. Here's the board with a cap and the original terminal removed. You can see the trace emerging from underneath the 51 ohm resistor. This is the one that needs to be cut. I drilled holes for the new 3-terminal connection block. The 2 outside ones are close enough to the original holes that a small solder bridge will make the connection. There's also a hole in the volt sense track, and I removed a large section of the original track. Finally, I removed part of the solder mask of the leftover track to allow a new connection to be soldered on. The new connection block can't be soldered in, of course, so it will be fixed with a drop of superglue. But before that can be done, it is necessary to solder in a small piece of wire in one of the original holes to serve as a wire to connect the underside with the track on top. The wire sticking out right now will be cut down, of course. Just make sure that nothing sticks out on the top, because that would prevent the new connection block from sitting flat. Here's the complete mod before putting the cap back in. You can see a piece of brown wire coming through the new hole and connecting to the SMD chain. On the underside, the brown wire connects to the middle terminal, which is the new volt sense input. The two outermost terminals are simply bridged to the original pads. With the capacitor back in, the board looks the same as before, except for the new connection block with 3 terminals instead of 2. I could have soldered the power board back onto the main board, but I decided to make it easily removable instead by soldering these pinheader sockets into the power board. They look a bit crude because I simply cut them from a long strip of 50. Using sockets, the two boards separate easily, and I can add the capacitor later once I received my SMD book. The two boards are back together. The use of the sockets raises the power board by 3 or 4 mm from the position it was before. It will still fit into the enclosure, but the back shell we need some trimming. But first, some tests. Here's the unit wired to mains with the volt sense connected by a little loop wire directly to live. In other words, it's like it was before the mod. The current transformer senses the live wire to the extension plug, which has an LED lamp connected. When power is connected, the mains voltage is shown. And when the LED lamp is turned on, the display shows the current of about 0.03, that is 30 milliamps, and a watt reading of 4.7 watts. I can't show the other readout modes because it would be far too dangerous to touch the module and press the button without a cover. So I decided to put that back on, which makes the display a lot more readable too. It's the same test as before, and the active power is shown as 4.6 watts. That's the power actually used by the light and which you pay for. I have no idea, by the way, why this button is labeled SAMCK. The rear is still open, so I still have to be careful. We now see 8.1 VA. This is the apparent power that you would get if you multiply RMS volts with RMS amps, and in case you wonder, I checked that the current is in fact 34 milliamps, but it can't display that resolution. With 34 milliamps, the 8.1 VA is correct. And another button press. Now we see the power factor, the ratio between real power, watts, and apparent power, VA, which is 0.5 something. Apparent power is what the lamp pulls from the grid during every AC period, but in this case almost half is returned right back into the grid during the same cycle. Real power is the part the lamp actually uses to make light, but all the gear like generators, cables, transformers and so on need to be sized to handle the apparent power flow. I don't have a variac yet, but this is the closest thing to show that AC volts measuring is now really independent from the AC supply. The blue transformer on the right has a split primary winding. That is just like a variac with a dial at midpoint. I removed the loop connecting the volt sense to live and connected it to the transformer midpoint, and indeed we see the expected 115 volts. I mentioned earlier that because I put the power board on sockets instead of soldering it back to the main board, it's now slightly higher than it was before. To make the back shell fit, it's necessary to trim the inner portion that sits on the power board by about 4 mm. You can see where I cut the two U-shaped portions down. And with that the enclosure can be clipped back into place. Time for one last check. Will it work for those folks using 60 Hz mains, since the spec did not say so? For this test I'm driving the secondary of a small transformer from an audio amp board as a speaker, so to say. The primary is connected to the module and an 1.8 kilo-ohm load resistor. The amp is driven by a 50 Hz sine wave, as you can see on the red multimeter. And now I change the frequency to 60 Hz. There's practically no change in the readout, so no problem, at least for sinusoidal voltages. Finally, I use my power meter mentioned earlier to measure the consumption of the module itself. Since the two showed quite different mains voltages, I connected my multimeter as well, and it turned out that my power meter reads slightly too high. The new module is more accurate and easier to read. I'm quite happy with that. As expected, the module's power board has a terrible power factor of 0.04. It uses just over half a watt of real power, but draws 236 volts times 0.06, that's 14 volt ampere apparent power. That would be really bad news when the electricity companies start charging consumers for apparent power. As long as that's not the case, the DL69-2048 module is a great solution if you're on the lookout for an AC panel meter that can be modified to measure from 0 volts up. Just treat it gently when getting the main board out of the case. Thanks for watching.